So I'd like to introduce now Deke Arndt from the National Centers for Environmental Information. There has been a lot of work going on over the last, decades in monitoring the Earth, seeing how the temperatures have been changing, and then now that we have a good handle on how those temperatures are changing, how are those temperatures and how is the atmosphere as it's warming up influencing our weather? How is it influencing extreme weather? Are we seeing more extreme weather? We know from the National Weather Service, Dr. Louis Ussolini has restructured the entire National Weather Service with his staff because we're seeing an increase in extreme weather events, and the Weather Service is looking to provide more impact-based decision support services to their core partners, and that means that they really want to deliver that information for decision-making processes. The same thing is going on with climate. Climate is influencing the weather. How can we get those fingerprints and attribute them to any heavy and extreme weather events? Deke has been doing some of that work. He's the director of the Observations Program at the National Centers for Environmental Information, and I'm really looking forward to this presentation. Please, those of you watching online, as you absorb this science and this information, please submit questions as well. We'll try to get to some of your questions, and those of you in the audience here, again, we'll be taking Deke, just like we are with Mitch Goldberg, into another room right down the hall to interview him with some of the questions that you have as you put together packages for your stations, and we will also share that with everybody after the program is done. So when you're looking for your content, Garth will have that in the room, the Iris room, so you can put together your packages for your live shots. So without further ado, Deke, thanks so much for joining us, and appreciate you being here.
Thank you.
Thanks.
All right. So first, I have a correction already. The date that the official global information will be released is January 18, not 20. So I'm afraid that might have been Freudian. So, I was a high school baseball player. I never made it past high school. I wasn't particularly that good, and I always wanted to go up to an at-bat with the bumper music that they play for all the big league hitters, and so the Gosar bumper music was the closest I'll ever come to having my own intro tunes. So we have changed this up a little bit. Dave wanted a little more focus on extreme weather and the relationship between climate and extreme weather. So the third bullet here, local and regional trends, kind of got axed a little bit. So that we got the skimpy version of that, and we piled a little more into the climate and extreme weather piece. But this is basically where we're going to go. Time permitting, I'll end with a story. And it kind of hopefully tries to bring some of this together and our mutual role as we work in climate. One thing that's always been a challenge for communicators like you guys and me is that climate just kind of unfolds over time. And tomorrow we're going to know just a little bit more than we know today. And it's hard to take a snapshot and kind of describe what's going on with climate. So hopefully we'll share some tools that will help you and us do a better job of just giving a running play-by-play of the climate system. All right, so I'm from Asheville. I don't know if this is one of you guys or not, but a lot of people retire to Asheville and spend an active retirement in Asheville. And a lot of weather data does too. And so we take the weather information from around the world. We're the world's largest, basically, weather library. And we put that information first and foremost into an archive for safekeeping. It's the taxpayer has already kind of paid for that data, so we protect it. And in the real time, groups like mine take the incoming data, the 1 or 2 day old data that's kind of made its circuits in the forecast models and the broadcasts, and kind of do a Lucy and Ethel watching the chocolates go down the conveyor belt and try to sort that out and compare it to the baseline that we're sitting on top. We're literally sitting on hundreds, centuries of data in this building. So one thing I always like to point out is, as times have changed, the 20th century and especially the 21st century, we've seen massive changes in technology. And so it's always a fun challenge to take the data that this lady was collecting back in the early 1900s and compare it to this stuff that came in digitally. She would write this down on paper and literally mail it to the Weather Service office, and it would find its way to a records archive somewhere. So the challenge is, how do we get these two data sets to play together, and how do we compare them with a straight face? And there's been a lot of tremendous science by folks upstream from us that do that. Anyway, so this is my particular group. We're the monitoring branch and the drought.gov US drought portal. I include this slide every time. These are amazing people. So we've got some meteorologists, some geographers, some physicists, some chemists, a couple software engineers, a GIS specialist. It hasn't it hasn't been a particularly easy decade to be a government climatologist. You know, you don't walk into a bar and announce yourself as a government climatologist and drinks flow. It's been a little challenging at times. It's been a little scary at times, and I hope my kids grow up to be like any one of these people. They've been amazing. They've handled that with grace and dignity and professionalism and a work ethic that's amazing. And I wish I had all 90 minutes to tell their story, because they've really, really been inspirational. It's been the best decade of my professional career to just be associated with these folks. And I'm a crier, so I'm going to move on. So a lot of these, I won't dwell on this. A lot of the information, probably 90% of the stuff that we're going to walk through today, comes from one of these 5 sources. So there's a more detailed, I think these presentations will be made available. So there's a detailed appendix, 5 or 6 pages of like where exactly stuff came from, if you want to sort through those as well. This is the commercial. So our monitoring branch will put out monthly and seasonal and annual public reports. We just about an hour and a half ago released information about this being the 2nd warmest year on record for the United States. I think we had 15 weather and climate events that totaled more than $1 billion each in losses. That's also, I believe, the 2nd most on record. 4 of those were inland flooding events, so that was really new to us. That was twice as many as we'd seen in any individual year. So the kind of pace of what we do in the branch is weekly with the drought monitor. I don't know if you pay attention to the drought monitor on Thursdays. We've got 3 or 4 authors of that in the branch. Monthly, which is kind of the pace that data used to come in, so it's kind of a legacy pace of ours. We would get a bunch of data in at once at the end of the month. Now it's digital. But it's a good pace to monitor climate. You know, to be making assessments of climate every day is a little silly and excessive. So we've kept that monthly pace to kind of update what's going on with the climate system. And then we do annual reports like the BAM State of the Climate. 2 of the editors sit in our branch, the lead editors, and that's where we try to pull in all of the information. But there's the URL on the top of the page. The U.S. reports are typically released around the 6th. The high-level overview and all of the data associated with the climate is released on around the 6th, depending on holidays and weekends. And then we follow up a couple days later with more long-form reports. You know, so if you these are more written for history's purposes. Here's what happened. Here's what we saw. Here are the trends. You know, that kind of stuff. And then a set of global reports is released every month, just after the middle part of the month. And if you're wondering why that's so delayed, it takes some time to get all of the data in from the different weather services around the world. All right. Okay, so that's enough of the commercial and the institutional part. Here's what's going on with climate. You've probably seen something like this a million times. So this is through 2015. We don't have the 2016 number on here yet, but this is the global average surface temperature. So this is useful for about one thing, and that is tracking long-term climate change. It's not particularly relevant really anywhere else. But it's a great metric to track long-term climate change, and it's a great metric to kind of introduce some of the concepts and gotchas and subtle variations in when you're analyzing climate information versus weather information. I'm an old meteorologist. I studied mesoscale meteorology and I got my master's in mesoscale meteorology, and I got out of grad school and I didn't know what I wanted to do, but I knew it sure as hell wasn't going to be mesoscale meteorology. And so I went into drought and went into climate, and kind of going from the mesoscale to this planetary scale has been really kind of neat to see the way everything interacts. So anyway, a couple things to notice here is there's generally an upward trend. So we're warming here at the bottom of the atmosphere where we take these observations. There's also a lot of interannual variability, so a lot of bouncing up and down from year to year. So it hasn't been this monotonic increase. There's still stuff going on in the planetary climate system that make year-to-year differences. I like to think of it as the long-term climate change element is like riding up an escalator. Over time, your floor is higher and higher, and the year-to-year stuff, El Nino, La Nina, the different ocean oscillations, they're like jumping up and down while you're on that elevator or escalator. So as your base, your floor kind of raises, depending on what's going on in the world, you may jump a little higher than you did previously. You may not quite make it to where you did, but that's kind of what's going on. It's this interplay between scales. And when you smooth it out to a decadal average, which you see in the pink bars, those are just decade averages for the decades, then you start to see a little smoother signaling. You start to see that the warming that really kind of accelerated in the mid to late 20th century. So 2015 was the warmest year on record by quite a bit. It surpassed 2014, which was at least nominally the warmest year on record, but it wasn't too statistically distinct from the others. But it's a data point. It's a data point on a long-term trend. 2016 through November was warmer than 2015, unless something really crazy happened in December, and I haven't looked at the numbers yet. 2016 is, again, nominally going to be warmer than 2015. So that's the big term, the big picture view. This is what that looks like on a map. So this is the same data on each map. One of them is presented. The map on the left is where were the parts in the world that were above and below the 1981 to 2010 kind of normal, so to speak. And the map on the right shows where each grid box, and we use 5 degree by 5 degree grid boxes, compared to its own history. So the one on the left is a number compared to a normal value, and the one on the right is basically like an expression of unusualness or rank. And you can see that 2016, which has been a very warm year, probably the warmest on record, there are still blue blobs that run around in there. There are regions that are colder than average, even in the warmest year on record. There is still weather that happens. There is still cold air that gets yanked from the poles. There are still blocking mechanisms that keep that cold air in place. There are still wet summers that are very cool that will pull these down. And so you can see a few things. One, 2016 was pretty typical of what we've seen in the last 20, 25 years in that land areas in the northern hemisphere, the high latitude Arctic northern hemisphere, were generally a lot warmer than the rest. It's the area that's warming the most. If you look at the map on the right, you can see that kind of scattered around the globe, and there's no real profound regional patterns. It's not like 2015 when we had an El Nino just dominating the Pacific and parts of the Indian Ocean. But you see big chunks of dark red. Those are areas that had their warmest year on record. And then the kind of medium pinkish red color is what we call much warmer than average, but is essentially a 10th percentile. So it finished in the top 1/10 of its history. The lightest pink, and if there is the top third, and then the white color is the middle third of history. The reason we throw these slides on there is there's two reasons. One, that global temperature is global and it isn't very relevant to people that live in places. So looking at it on a map is usually a way more relevant way to look at it. And then also to indicate that, there in a year there are kind of pluses and minuses and ups and downs. And when we talk about these big global indices, they are global aggregates. They are statistically aggregated. All right, so how have we been trending since? These are the same scale. It's a little sharper since the last 30 years. But again, the most rapid warming is going on basically in Eastern Europe and then along the Arctic coastal land areas. So that's where we see the most warming over the last 30 years. You can see a little more noise in the 30-year sample than in the 100-and-something year sample, and that's very typical. A lot of climate assessment is trying to find when the noise starts to dominate the signal. 30 years is pretty safe. And you can see in a lot of the world it is getting warmer. We'll talk about the Arctic amplification, but basically a combination of positive feedbacks are helping the Arctic warm more quickly than the rest of the planet. However, again, no one was found dead under a trace of global temperature, right? It's a metric for scientists to track global climate change, and what matters is what goes on throughout the climate system. So one of the honors I've had recently is this will be my, I think, 8th year to be one of the lead editors of this State of the Climate series. You get it with your BAMs in the summer. It's gone from this thick to this thick. The last 6 years, I've been the second lead. Jessica Blunden from our branch has been the lead and done a great job. But this comes from around the world. We have about 450 authors from 60-something countries, and we try to assemble this kind of diagnostic of the climate system. And the next 8 or so slides that we're going to go through pretty quickly are all pulled from this BAM State of the Climate. And we like to think of it as the annual physical of the climate system. So this is the doctor's chart. These are the vital signs. We don't make any real attempt to attribute these changes to anything. We're just like, hey, here's the latest update of all of the different pieces of the climate system, from river discharge in Africa to the stratospheric temperature to sea ice extent around the Antarctic. This is the big set of charts. One of the things that we showed, or that we found, is that generally what we would expect to increase in a warming world is increasing. That's stuff like temperature, the amount of energy in the ocean, sea level, ocean heat content, and especially significant humidity, absolute humidity. And then the frozen stuff is getting smaller. That's basically what the cartoon version of what we've seen in the 25, 26 years that we've been doing these State of the Climate reports. This is just a map of where the folks came from. So we're constantly working to try to bring more authorship from around the world, because some of the things that are happening regionally are the most interesting and the most relevant as we go. If you want to peruse 250 some odd pages of stuff, there's the URL. But it's meant to be a desktop reference. No one in their right mind, other than Jessica and myself, would read it from cover to cover. But it's a nice place to go look stuff up. All right, so one of the things that is great, and Dr. Goldberg talked about this, is we have kind of multiple ways of taking and analyzing overlapping observations. And so this is just 4 institutions. One of them is us. One of them are the folks up at GIS at NASA, the Japanese Meteorological Agency, and a group, or the Met Office, the UK Met Office. And these are the 4 analyses of global surface temperature from those groups. And basically they have different ways that they analyze, different ways that they combine data, different ways that we fill or don't fill data sparse regions. Some of us are more aggressive, some of us are more conservative. But basically all of the data sets, all of the analyses are singing the same song. They just hit different notes along the way. So there's essentially 4 relatively independent analyses that say, yeah, surface temperature is increasing. And we, just like any professionals, all try to compete with each other in a friendly way to come up with the best estimate of what's really happening. And so we try to pursue the truth and do a little better than keeping up with the Joneses and improve. So again, these are 4 data sets that indicate temperature. And then this is the last we'll spend on global temperature, but I wanted to put this out here because outside of the scientific community, there's a lot of distrust of the adjustments that we make and other groups make to the data that come in. So there's a lot of suggestion and innuendo that scientists are manipulating the information to increase the warming and that is somehow better for the scientists. I haven't figured that out, why that is yet, but the reality is we are pushing the needle in the opposite direction. So the outlier trace on this set of graphs is the uncorrected, the raw data. And if we were to just let the data speak for itself without making the necessary adjustments to it, it would actually be a higher warming rate since the early 20th century. And this isn't something that is often shared. So I share it with you in that if we were really up to something, we are all pushing the needle the other direction. And it turns out that the reason for the rather large adjustments in the 20th century that made the warming rate more modest in the corrected version had to do with the evolution of sea surface temperature observing technology. So in World War II, we really went very quickly from guys throwing buckets over the sides of ships and pulling them up to measure sea surface temperatures. They didn't want to get shot while they were doing that, so we started using engine room intake. We, being the fleet, started using engine room intake to estimate sea surface temperature using the ERI value. Engine room intake is a warmer observation because it's going through the plumbing of ships that sit next to a big engine room, so it's warmer than the bucket observations, which when you throw the bucket over the side and pull it up, you get some evaporative cooling. So so we correct for that, and that's that big correction that you see before World War I. Turns out that ERI observing is a lot cheaper and more efficient, and so basically the world fleet stuck with that afterward. That's pretty nerdy, I'm sorry. That was a data center guy. All right, so this is going to be kind of the rapid fire round, just as a background for what's going on the planetary scale. The greenhouse gases that are driving the warming typically reach a new record high each year. This is something that we see almost without fail. Each year has higher greenhouse gas concentrations than the past. As you well know, probably methane and N2O are pound for pound actually way more potent greenhouse gases than carbon dioxide. The reason carbon dioxide is the greenhouse gas and gets a lot of attention as the greenhouse gas is because there's a lot more of it. We measure it in parts per million rather than parts per billion, and it lasts a lot longer. It's a very stable gas. It doesn't chemically react. It's happy as CO2, and it's hard to unmake it as CO2. There's a reason they package some food products in CO2. It's a very neutral gas. So it sticks around a long time. It sticks around for centuries to double-digit centuries in the atmosphere, whereas methane and N2O will break down decades to centuries. Methane is becoming more important in the big picture. This graph on the right shows the forcing, the cumulative total of the extra energy that's being re-radiated back to the surface of the planet based on the cumulative contribution of all these greenhouse gases. So the 1990 line is drawn there because that was when the Kyoto Protocol was proposed, and that was kind of the baseline. So this index, that 1.38 that you see at the top of the graphic, says that we are now providing 38% more forcing through greenhouse gases than we were in 1990. It's an additional roughly 3 watts per meter squared. So it'd be like having a 3-watt light bulb every meter around the planet on constantly. That's what's contributing to our forcing. And CO2 is more than half of that. All right, promise we talk about the Arctic. So the Arctic is warming faster. So the global temperature average is in gray in this graphic. It's the same data set that we looked at earlier. The Arctic is taken as the 60 degrees and poleward piece of that, and we've seen a lot more amplification, and that's due to the retreat of sea ice. So sea ice is very, very, very reflective. It bounces the solar energy back into space. And so when it disappears and is kind of replaced in the system by darker water, That absorbs the sunlight, which is a positive feedback, which contributes to warming through the reduction of albedo. Same with snow. So snow in the high sun seasons is really retreating in the northern hemisphere. And the same with shrubification is kind of the term of art of the Arctic. So larger plants that tend to be a little darker are growing instead of these tundra lichens and sedges and grasses that we see in the tundra. Now we're seeing shrubbier growth that can stick up above the snow and again reduce the albedo. So the Arctic is the crucible of change for the planet. Sea ice is retreating, particularly in the high sun seasons. So the red graph is basically the September average of the Arctic sea ice extent, how big a footprint it is, from the late 1970s through last year. We went way down there again this year, not quite the record, but it is retreating more every year. And again, based on weather patterns in the Arctic, it's not a general decrease. What's driving a lot of this is we're losing a lot of multi-year ice. So the graphic on the right shows how much old ice was in the Arctic from 1985 through last year, and the yellow and the pink and the green represent multi-year ice, which is a lot more resilient to melting. So older ice is thicker ice, it's harder ice, it's more resilient ice, and as the older ice goes away in the long term, the ice that's kind of left is first-year ice, and it's relatively soft, so to speak. Snow cover extent, forgot about that. Snow cover extent is, again, we track snow cover extent in the northern hemisphere because that's where all of the planet's seasonal snow is. And the high sun seasons are tending to see the most retreat of snow cover. So the summer to late spring, early fall is seeing the most retreat of snow cover. And then, frankly, the winter seasons are relatively flat. So the snowy times of year are not getting really any more or less snowy as we go, but we're seeing this late spring, early fall. That's important because the sun's high in the sky, and that snow that would normally be there, at high latitudes in the northern hemisphere reflecting sunlight is not there anymore, again, kind of contributing to the warming. Permafrost is changing. That's an issue in the Arctic. It is becoming active where it used to not be active, which means it used to be permanently frozen. Now some places are now thawing seasonally. That's really tough if you've got infrastructure in the ground that is depending on frozen soils. It's tough when you're a coastal village and the thawing of the permafrost leaves your soils vulnerable to wave action. And so we're seeing big-time coastal erosion in some zones in Africa, and they've had to relocate several villages, which isn't just the living people, it's the ancestors, too, that need to be moved, and the houses and the stuff. It's a very costly exercise, and not an easy thing to do from a personal level, to leave what you've known behind. This is, I think, the last of the kind of depressing global metrics. The sea surface temperature anomaly is going up. 15 was a record in basically all three big ocean metrics. Sea surface temperature averaged around the planet was the highest on record. It was driven by the Pacific, which had a really strong El Nino at the time, and the Indian Ocean, which was crazy, crazy warm. Sea level, which goes up as a combination of, as the water warms, it expands, and also as land-borne ice melts and runs off into the oceans, contributes. So sea level was at its highest. And then ocean heat content, which is where about 90% of the warming goes, is in the upper layer of the ocean. Ocean heat content was record high, and that is that graph is zettajoules, which is 10 to the 22nd joules or 10 to the 21st joules. It's a measure of calories or energy that is stored in the upper 700 meters of the ocean. again, that's about where 90% of the warming is being experienced now. Yeah. Yep. Zettajoules, yeah. It's a big number, a lot of zeros. And this, I won't go into ecosystems because I won't even pretend to be an expert in this, but a lot of what we've seen from authors that actually know what they're talking about in the Banff State of the Climate is, just the disruption of living systems. So things need to move where they are adapted for those climate conditions, and that's typically poleward or upward, in a 3 out of 4, 4 out of 5 kind of way. Species are getting stressed to move poleward or upward in altitude, and a lot of times there are barriers to that. And here's an example on the left of about 10, 15, 12 years ago, where some specialist Arctic species are getting basically pushed off the shelf by more generalist species. And the rule of thumb that we've seen are, warmer species and more generalist species that'll eat anything and live anywhere, are doing really well with the climate change, as climate changes and their environment changes. The specialist species, either cold water or cold air species or cold ground species that have very specific diets or very specific habitats, are the ones that are losing. So, and this is just an example of the Arctic fishes in purple here are shallow water species. Well, they're getting shoved off the shelf and they can't live in the deep water. So we see this playing over and over and over and over and over again in a lot of the sidebars that are in the Banff State of the Climate. And then finally, we mentioned upper air temperatures. If there was a smoking, we know why climate is changing because we've learned physics over the last 6 or 7 centuries. But even if we didn't, if there was going to be a smoking gun in the observations, this is it. So what you're seeing on the left is the temperature of the lower troposphere, which is up to about 6 miles above the surface. The folks in the room all know where that is, but maybe the folks online don't. So this is the lower part of the atmosphere where we live and where the weather happens. And basically, according to the radiosondes, which are weather balloons, according to the satellites, and according to the computer models, all 3 of those families of observations or analyses are showing warming in the lower troposphere, just like we'd expect. All 3 of those families are showing cooling, which is the right panel in the stratosphere. So we can't preferentially warm the bottom of the atmosphere and cool the top of the atmosphere without changing the composition of the atmosphere. So if there's any real smoke, and you can see the effect of a couple of volcano events that cause temporary spikes in the stratosphere as well, we won't get into. But this is it. This is the smoking gun. This is the sun. If it were the sun being brighter and warmer, it would heat the whole system. It wouldn't just heat the troposphere while the stratosphere is cooling. This is the smoking gun. Yes, sir.
Before you leave this,
yeah.
So, Jim Gandy, WLTX in Columbia, South Carolina. So basically, we know why it is warming. I've seen comments already, well, the climate is always changing. Well, of course it's always changing, but it changes for a reason.
Right.
It just doesn't change to be changing. And we know that it's because we're putting more greenhouse gases up into the atmosphere. Mm-hmm. And good night, you've already shown us so many different things. So basically, we know why it is warming. We can put that to rest.
So, and I think science has. The public discussion has other influences in it, and it's more complicated in a lot of ways than the discussion in the safe spaces of science. But yeah, so and the climate has changed, and it has changed more than this in the past. But what we know, what science is helping us understand, is why this change is happening. And we know why this change is happening, and we know that this change is a lot faster than almost every change we've seen in the past. And we know that this change is the only change since we've been walking around speaking language to each other as humans. And so that's why this change is more important to our species than all of the other planetary changes that we've seen in the past, because we're living in this, and we have systems, agricultural, economic, infrastructural, that depend on our climate, and catching up with the climate is going to be a challenge for us. Thanks. All right. This is the part that got cannibalized, so we could talk about extreme weather. But 2016, again, was the second warmest year on record for the U.S., including this map for two reasons. One is it was really widespread. This was, although Alaska and Georgia were record warm, this was a year, 2012 was record warm because the middle part of the country was really warm. It was dealing with drought and it got really hot, and it kind of drove the picture. This one was one of those, like, win the decathlon by finishing third in all the events kind of years. So everywhere around the country it was like second or third warmest on record, and that was kind of unique by looking at it. And then the other thing, the maps on the right show afternoon temperatures, departure from average, or how much different they are from average on the top, and morning or overnight temperatures, minimum temperatures on the bottom. And this was really a year where the recent trend of the last 10, 12, 15 years, where we've seen minimum temperatures kind of outpace maximum temperatures. The rule of thumb in climate, especially in the U.S., is the cold places are warming more than the warm places, the cold times of day are warming more than the warm times of day, and the cold seasons are warming more than the warm season. And that'll win you 3 out of 4 bets, and then you'll lose the fourth one. But that's generally what's going on in the U.S. And this was a year where it was the second warmest year on record, kind of carried by the fact that the minimum temperatures were the warmest on record. And so we're seeing this, and we'll talk about extremes here in a minute, as a trend in the U.S., no doubt about it. This was an exclamation point on that. This is the same information, but in that ranking style that we talked about. So the places that are red had their warmest year on record. The places that are orange had something in the top 10%. Yes, sir, Greg.
I'm sorry, Greg Fischel, WRAL Raleigh. What is it? The ACIS database, that interactive thing where you can look through all that. At RDU, exactly what you're talking about is very clear, that almost every month the minimum temperature anomalies are warmer than the other.
Yeah.
But doesn't urbanization also have a similar signal? And so I've tried to make an effort to look at more rural sites.
Yep.
And the problem I run into is that there's so many missing days of data, or maybe they only became an ASOS in the year 2000, so I can't go back 30 years.
Right.
What are the kinds of corrections that you all try to make, or accounting for that?
Yeah, so first of all, I want to acknowledge that those are two legitimate issues, right? So there is urban heat island effect in large urbanized areas, and it's a real thing. But also that this data that we're looking at has been corrected for that. So basically the stations that are showing warming that is accelerated relative to their more rural peers have been corrected for that. However, urban heating, even though it's not related to greenhouse climate change, is climate change. It's not related to greenhouse gases, but it's a legitimate thing. And I think a lot of times scientists have been pretty quick to brush that under the rug because it's basically irrelevant to the trends that we see because we correct for it. But it's an actual thing. Summer times are getting a lot warmer in metropolitan areas, and if you have a lot of people in metropolitan areas that don't have access to air conditioning, and summer minimum temperatures are going up, that's stressful. That's a public health, economic issue. That's a horrible issue for the people that are impacted. If they're working on roofs, or if they're having football 2-a-days on summer mornings, I mean, we are seeing warming in the metropolitan areas. Did I overkill your question?
No, that's
sorry. All right, thanks. So this is a commercial. I'm sorry, this is one more commercial. a lot of times, we talked about in Dr. Goldberg's session that the gee whiz neat kind of stuff that you would like to see kind of land in your lap. We often put these in our supplemental information that are related to our monthly and seasonal reports. So these are time permitting. If we see neat things that we think might be more attractive or digestible for real people that just kind of want to see what's going on with the climate without worrying about climate change, but stuff like this. This was inspired by, I think on Facebook there's always the, what is every county's favorite football team kind of maps, which we're all geeks, we love that stuff. So we're running a series this year of like when was your warmest January or coolest January or wettest January, and we're going to be running those all year as supplements, and they're kind of fun. You may not particularly care for our color palette selection, but hopefully you can go in there and change that. But it's interesting, so one of the things that's kind of cool is 1919, which is this color here in the Gulf states. That is still the warmest autumn on record for the Florida Panhandle, southern Alabama. But nationally, it was actually one of the cooler autumns on record. So it's just kind of a neat way to kind of continue to help folks understand that what they're experiencing in their backyard may not be what's going on in the rest of the world. And the rest of the world is certainly a valid concern and has big implications, but what's going on in their backyard is totally legitimate for the individual. And so we've tried to provide 3 or 4 of these kind of gee whiz things each month. Autumn at a glance, just because we had data through November, our September, October, and November autumn, which breaks on the clusters of 3 months, because that's how data used to be reported. It's also puts June, July, and August, the 3 warmest months in the same season. Had our second time in a row to have our warmest autumn on record. So if you think autumns have been pretty warm lately, you're right, nationally. So just to, and I'm tempted to go point at things. So if you want to go download this data, so you can go to this Climate at a Glance page, and you can zoom into your state or your climate division, which is a sub, there's 5 to 10 climate divisions in each state. Or you can go to some cities within your state, and you can make this graph for whatever season, whatever, there's 9 or 10 variables that are some expression of temperature or precipitation or drought. And you can make a time series. And if you don't like our ugly purple knobby-kneed time series graph, you can download the data. And here's some formats. XML, if you have an XML geek in your production shop. This is the one almost everyone uses, which is the CSV, the comma-separated variables, and the JSON, which is a technology that has outpaced my brain. So that's apparently really cool for some people. So you can download these, get this information into a graphics package that looks a little better than this and reflects your station as well. Yes, sir.
You kind of know this is coming already. I'm Joe Murgo from WTAJ TV in Altoona. How many of you guys actually do use NCDC information and go to their website often? Okay. What's the one comment that you guys think about when you use their site? Easy to use? Yeah. Okay. There were some murmurs of no, just to say it on the microphone. Well, actually, Deke said it would help if we kind of made it, instead of just sitting and bearing and hiding it and using other things, to actually tell them and email him, right?
Yeah,
about it.
And we have, and it's not just for the monitoring group, which does kind of the real-time stuff, but if there are certain products, so if I can kind of tell the story of NCDC. So we've been doing what NOAA now calls use-inspired science for about 60 years. But we were doing that when data was on paper and when our clientele was agriculture, energy, and kind of consulting climatologists. And now data are really important across the economy. Retailers Think of a big retailer, and I will tell you they're one of our best customers. They're pounding our servers. And so we're doing really good for these machine-to-machine automated go grab the data with no human contact piece, and we're doing really good with our traditional constituencies. But where we're really struggling is how do we present this data more usefully for the emerging customer, and I would include all of you in that. The people who aren't running models based on our data, which is what the retail and the agriculture and the energy people do, but the people that need to get in there and grab some data and beat it up and make an analysis, that's the area where we need to grow. So I'll echo what Mitch said. If you can tell us what you need, what's your top 10, what's your top 5, what's the most frustrating aspect, what's working, please let us know. And we will continue to try to get better, to get into this digital age. All right. Quickly, change since 90. How am I doing? Change since 90. Different parts of the U.S. are warming again. Generally speaking, the north and, in this case, the southwest are warming more rapidly than the central and southern plains and the southeast. It has been suggested, but it certainly isn't completely consensus science, that a lot of the lack of warming in the southeast is due to greater humidities and greater precipitation. I think that makes sense meteorologically, but I don't think that has been run through all the paces that need to be run through before we can, pound the table and say this is settled science. So, this slide is only on there to underscore the more global trends versus the my backyard trends. And in generally, it's just a rule of statistics that the smaller you focus, the more narrow and the smaller the data sets, the more noise you see. So what this has is, in a thick green trace, is that same old global temperature trace that we looked at earlier. And then in the dark blue trace, that's the U.S. temperature. And in the dotted red trace, that's the same for Oklahoma, the state of Oklahoma. And you can see as we go to smaller scales, it gets a lot noisier. And you're going to find that to be true. So if you're looking at the global temperature and you're looking at the Charlotte temperature time series, and you're like, man, why is this wacky and all over the place? It's basically a universal truth in the data. It happens everywhere. All right. So we talked about sea level rise. What really, again, sea level rise is just this big kind of number that's for tracking. So, what does it mean? And Dave asked, what does it mean? So sea level rise is important for a number of reasons. One of which is this clear sky flooding that we're seeing along the southeast. So if you have friends in Wilmington or Charleston or Norfolk or Baltimore or Miami Beach, you've seen a lot more of these kind of tidal flooding events where you have high tide and onshore wind and maybe a warm current nearby, and you get these ankle-deep flooding events that don't kill anybody and rarely hurt anybody, but man, when they happen over and over again, they're disruptive to the economy and they're disruptive to infrastructure. And so there's a lot of places in the U.S. due to sea level rise, and then in some places due to subsidence of the soils, are really, really dealing with this. John, I know you probably are seeing this quite a bit. So this is another manifestation of what we're seeing. Yes, sir.
Kent Derhart from St. Louis. That's the first time I've heard anybody mention subsidence in this discussion. Is there a tie to climate change with that subsidence?
I don't think so.
Okay.
No. So the subsidence is either kind of natural, kind of what continents do, or it has to do with the channelization of streams out into the ocean, so they can't deposit their sediment and kind of restore the coastal areas. But the Pacific Northwest and Alaska is actually rising, so it's isostatic rebound from being covered in ice, tens of thousands of years ago. So the subsidence varies around the planet as well. Yes, sir.
Hey, Deke, Howard Bernstein, WUSA. you able to quantify how much subsidence versus sea level rise on these nuisance flooding warnings that we're getting, or is that just mentioned there because it's like in the Norfolk area, for example, it's a big player there, but for a lot of areas it isn't?
So there's a technical report that this links to, and I won't pretend to be an expert, but it's a combination of three things. It's local subsidence. There's a lot of bathymetry. The shape of the ocean, the coastal floor really plays a role in these tidal flooding events, and then sea level rise as well, and then onshore or offshore wind. But they lay it out a little better than I can in this technical document. Yes, sir.
Hey, Howard, this is John Morales from NBC6 in Miami. So the AMS recently put out their relation to weather with climate collection of papers, and I'm reading a month ago. From the AMS, there's a paper there of the increase in sunny day tidal floods in South Florida, and they do quantify the subsidence for that area, and it's only 4% of the entire number of.
Most of this is obviously from warming and thermal expansion.
Right, at least there anyway. I mean, it's specific to that area, right?
Thank you. All right, and then finally, this blew me away. So this is Barrow. This is again an indication of multiple factors at play. So, but this is a time series of the September-October temperature at Barrow, and I think this is really interesting, and I chose it specifically because this is the time of year when sea ice used to be very close to Barrow, which is on the northern slope of Alaska. It's the northernmost kind of settled place in the U.S. So in September and October, they were typically icebound or near icebound, actually year-round. But now in September and October, the ice retreats a lot farther north into the Arctic Ocean than they used to. And you can see this new floor, this new regime at Barrow, which they may welcome. I don't know if September and October are a little warmer there, but you can definitely see a step change in this graph. That we used to see kind of warmer, what we call autumns and colder ones, but we don't see the colder ones anymore. And this is, again, a reminder that the climate change that we measure in a place is not, every day is getting a degree warmer. It has to do with, we're spending more days on the warm side of the front, or we're spending more days with precipitation producing storms. And this is a nice example of that. Once the ice went away, they kind of jumped into a new climate regime. All right, this is the fun part. So climate and extreme weather. This is since 2010, the states that have set their record for the warmest or coldest or driest or wettest, whatever, on their record. And I think it's pretty instructive to look at this. So the months are the individual months. So just going off the top, for March 2010, New Jersey and Rhode Island had their warmest March on record. And then their seasons, spring, quarters, annual, stuff on the right. If you take your glasses off and just look at the colors on this, you see a lot more red than blue, but there is still some blue left on there. And you see a lot of green on there as well. And this is really consistent with both what we'd expect in a changing climate and what we've observed in other ways in a changing climate. State records by themselves are kind of a novelty, but you get this much information in front of you, and it is instructive. So we see a lot more blue or a lot more red than blue recently. And this is, again, if you're looking for national patterns of how many records were broken or not broken in a day, this is a nice, friendly little tool, and you can dig in there and get a map of them if you want. But I wanted to point out that the ratio of warm records to cold records was about 5-to-1 this year. These are individual stations that set daily records for that day at that station. And then, again, minimum or morning time temperatures outpacing maximum even in the warm places, even in the warm records. It's that cold time of day, cold time of year, cold part of the country that is warming more rapidly than the rest. It's also global. We're seeing an increase. in the number of warm days, those days which would have fit in the top 10% of history, and we're seeing a decrease in the number of cool days, those days which would have fit in the coldest 10% of history over time. This is the series I think you were talking about, the BAMS explaining, or the BAMS Extreme Weather series, and this is how we, this was kind of an assessment of what do we know about the relationship between climate change and extreme weather, and there's two axes here. As you go up the axis on the left, that means what do we know from a science standpoint, the relationships that we've determined as a scientific community. The higher up you go, the kind of more confident we are that we think we know what's going on. As you go from left to right on this graphic, it's regardless of what we know about it, how are we able to detect it through observations? You know, how detectable are these signals? And there's no surprise, for the most part, the things that we observe really well are the things that we know quite a bit. But I guess the punchline of this is big rain, big heat, and big cold are the things that we feel the most confident about, the relationship between the way those are behaving, and we'll go into the details in a second, and long-term climate change. And we feel pretty good about floods and droughts as well. And I actually was an author on one of these papers, and I wrote the piece on ice storms, which is both the least confident and the least detectable from the series. And I'll put it this way, my section was a sentence when the paper got done, and it was basically tough to call, ice is hard to measure, and there's all kinds of regional stuff that goes on. So, but you know, as we go along, the things that are more common, the things that are observed more and more regularly, are the things that we're the most confident about. It's just like a meteorology problem. All right, so here's some of you have seen this before. We'll jump into the literature here. This is the seminal piece of literature from the mid-'70s that defined the relationship between weather and climate. And it was written by Stallone and others. And basically, that guy's weather and that guy is climate. And, you know, so this is, I say this over and over, weather throws the punches, climate trains the boxer. We don't know what punch Rocky's going to throw with 2 minutes and 7 seconds left in the 7th round of his next fight. But we know if Mickey's his trainer, he's throwing a lot more left hooks. And that is, in a nutshell, the relationship between weather and climate. It's a coach-athlete, teacher-student, parent-child, mentor-apprentice kind of relationship. It is a long-term influencer of behaviors rather than a hands-on-the-knobs and dials controller of immediate outcomes. And we typically measure this statistically, using statistical tools rather than dynamical tools. Now, we try to understand them using dynamical tools, but they show up in statistical ways over time. To beat mid-century pop culture to death, this is, I have a 14-year-old boy now, and he is kind of impulsive. He has a short attention span. He's a great kid. I think there was another teenage kid in here earlier. So he's really tuned into his immediate environment, you know, like, you know, the things that happen around him can make him do extreme behavior. He can do extreme behavior if the right set of ingredients comes together. And the beautiful thing about him is he forgets quickly and moves on. And if we hadn't named him something else, we would have named him weather, right? That's weather. That's what weather does. And that is in a stable climate, right? But what happens when we change the climate, okay? So, well, here's the thing. If we change the climate, he's still going to be impulsive. He's still going to be really sensitive to what's going on immediately around him, whether he's hungry or whether someone's being mean or, you know, whether he's tired, didn't get enough sleep, or whatever. And he'll hang out for a few months at a time with his new buddies, La Nina and El Nino, and they'll kind of shape the way he behaves. But in this new climate, the ingredients for the extreme weather, while the ingredients are the same, they're coming together at different frequencies and at different paces, and they're showing up in kind of new arrangements. And that's kind of climate and weather in a nutshell. his days are driven by the same, even in this new climate, his days are driven by the same factors, but the trajectory of his life has changed. And that is, again, mentor, apprentice, parent, child. That's how weather and climate are connected there. All right. And I'll move quickly, Dave. We got about 20 minutes left. So here's this. Actually, the rest of this, the next 10 minutes or so, is just like, what are we seeing in the different big weather, and to the extent we know, why are we seeing it? So this is a theoretical graph of what we would expect to see in a warming world. So the bell curve moving to the right shows a climate influence shifting from what was a normal climate into a new, warmer normal climate. And we would expect to see more weather that used to be classified as hot and more weather that used to be classified as unprecedented. And we would expect to see less of what we used to call cold. And that's exactly what we see in the data. So the theoretical shift is played out in the data. So this is looking at the 1951 kind of mid-century baseline of the temperature values that we've seen, and then each of the subsequent graphs is a decade after that. And you can see when we look over the northern hemisphere, we see that moving to the right, and we see exactly what the theory would have implied. So that's what we're seeing. Big heat is increasing, and this is, I should confess here, this is one of the more dramatic maps, and I chose it because it's one of the more dramatic graphs. The other seasons aren't quite this impressive in the way they're changing. But this is a graph of one of the components of our climate extremes index, and this particularly tracks the size of the footprint of extremely warm minimum summer temperatures across the CONUS. So how much of the U.S. is having summer morning temperatures that are considered extreme compared to history? The larger the red graph, the more of the U.S. is involved in that scenario. The larger the blue bar, the more of the U.S. is having extremely cool summer mornings compared to history. And you can see a profound trend here. Summer mornings are getting warmer, and the widespreadness of extreme summer warm mornings is getting bigger. And if I were to talk with you and we were all meteorologists, we would talk about the blocking patterns and the southerly flow and the moisture regimes and the ridging, and we could talk strictly in meteorological terms about each of these summers and what's set up to cause this big patches of red on the map, right? And we would be right. We would meteorologically be accurate. But when we think about it climatologically, we would look at that last 20, 30, 40 years and say there's something going on here. There is a larger influence of what's happening. And we talked about summer minimum temperatures. Public health, access to air conditioning, people that work outdoors, people that recreate outdoors, people that do have air conditioning and run them more during the night, during summer, are consuming more power. I mean, this is there's a lot to unpeel here beyond just some red bars on a graph. Our summer mornings are getting warmer dramatically. Extreme events, so individual things that we count. We have a great situation. I think I'll go ahead and spoil a graphic in the future. Tornadoes are a great example. We've seen this huge uptick in the number of tornadoes that we observed since the early 1950s. And it's almost entirely a consequence of the fact that we're just way better at predicting and warning and going and verifying smaller tornadoes. And there's really no climate signal in there. So things that we measure, like temperature and precipitation, we can kind of use the data in the more raw form. But things that we count, like hurricanes, tropical cyclones, big hail, tornadoes, we need to step back and look at the ingredients. How are the ingredients changing? Are we just getting better at observing these, or is there a climate trend? And looking at the ingredients helps remove us from that. So precipitation is the result of big rain rather than extreme precipitation. in general, this is another one of those 2 out of 3, 3 out of 4 kind of things. Wet places and seasons and things that happen are getting wetter, and dry places and seasons and dry episodes are getting drier. And then we have a lot of great data for this. And so we are seeing, indeed, an increase in big rain. And so this is a map from the National Climate Assessment that basically shows the percent increase in the role of really big rainfall events in the annual water budget. And we're seeing 2 significant changes, especially east of the Rockies, in big rain. 1, the big rain events are getting bigger on average. And 2, the annual water budget is becoming more and more driven by the big rain events. Does that make sense? So big rain events, individual events, are taking up bigger chunks of the annual budget. Yes, sir.
Howard Bernstein again, Washington. Maybe I missed it. What's the time range on this?
This is I can get you the exact number, but
Give me ballpark.
It's recent decades versus the middle of the 20th century. I think 1961 to 90 was the base period, and it was since there, but I'll go look that up. Yes.
Okay, Deke, Joe Murga from WTAJ-TV. It's interesting, the big rain events, and we've had a couple of really big disasters in central Pennsylvania in the past decade, where parts of towns just totally wiped out with floods. The interesting thing is we're seeing big rain events, but overall, we're in very dry patterns. That is it's very hard for people to comprehend too.
So I think I didn't ask him to say this, I promise. We're going there. So the next slide shows that all of these recent years, so we've had a real upsurge in the number of billion-dollar big rain events in the U.S., and these have occurred during pretty droughty years in U.S. history. And it's this weird counterintuitive and fact that we are getting a lot more big rain in big doses. There's a lot more time and space between those events, and that sets us up for drought manifestation. And the atmosphere is warmer, which pulls more water out of the ground that makes things droughtier too. So it's this combination of factors. Thanks, Joe. I'll buy you a beverage afterward. That's it. Yes.
It's a bigly word.
This is just a graphic that Greg Carbon could do this a million times better than me about the tornado trends are mostly due to improvements in our ability to capture them. Hurricanes and tropical cyclones, the short version of this is it is not real determinative of whether we will see more tropical cyclones. It is fairly well agreed that the average tropical cyclone will get stronger over time, but I don't think that's even a slam dunk. What is known is with higher sea levels, 1985's Category 3 storm is not going to do as much damage as 2016 Category 3 storm, because 2016's Category 3 storm is going to be pushing a lot more water due to higher seas. And we saw this with Sandy as a classic example of the consequence of higher sea levels. I'll skip the violent local. The only reason I put this slide in is one of the cool things about my job is I get to validate the national hailstone records, so I have all these plaster casts of hailstones in my office. It's great. But in general, there's competing factors for violent local weather, meaning hail and tornadoes, and the instability is increasing and will likely continue to do so on the climate scale. And shear over the climate scale is decreasing. So they're kind of at loggerheads. And so there's no real clear signal on whether we don't find a signal, and we don't know whether we will find a signal in a relationship between climate and big weather, big local violent weather. All right, so I ripped this off from Stephanie Herring, my colleague in CEI, on how we go about, this is a brand new kind of area of science, how we go about connecting something that happened with climate change. And so in science, your question is always more important than your answer. And so this attribution science, and it's still in its toddler years. When it was in its infancy, the question was, did climate change make that thing happen? Which is an impossible question to answer. And so now that this science has evolved largely through her work and a small number of colleagues, the questions that are more productive are, has climate change increased the odds of something like this happening at this time, at this place, during this time of year, or has climate change increased the odds of something this big happening, or is it climate change basically making these things potentially more big? And that's where the science is going now. This is a great slide of hers. So a corollary to real life is from your daily commute. You know, it's if you go faster, you're more likely to be in an injury-causing accident. No doubt about it. You know, just statistically over time, that's the climate change piece, right? So if we warm the world, in the long run, certain things are going to be more likely. But if a specific accident occurs, it could be these very local things like a distracted driver. Maybe you were distracted. Maybe another, you know, maybe something just bad luck, you know. So the challenge is separating kind of these two factors, and that's what they do. And they do two, and some would argue three kind of main approaches. One is they look at the historical record and determine whether these things, whatever they're looking at, are getting more common over the historical record. And that's one way of looking at it. The second way they do is a more dynamic approach, which is they use a modeling approach and they turn on and turn off climate change, and they see how the models would statistically handle this type of phenomenon over time. And they usually come up with things like, this heat wave in such and such a place during such and such a season was 48% more likely in a warming world. And their answers look a lot like that. The things that they need are just like a lot of science needs: good data, good science written into good models, and a sound physical basis. That's the good science. And here's how they've kind of, and I'll leave this up here just to kind of explore yourself. So the left pillar is, do we have the data? The middle pillar is, do we have the horsepower, the computing power to do it? And then the right pillar is, what do we know in the science? And again, big heat and big cold are where we feel the best. And those things, and then the more local, the smaller phenomena, the stuff with less data, are typically where we have the least confidence. And that's where they're breaking new ground and doing neat things. And I don't think she'd mind me saying that. They'll look back in 5 years at what they're doing today and kind of giggle. They're improving that rapidly. It's a really cool field to watch evolve. All right. So this is beating the same horse to death. This is how good we think we are at attributing big events to climate change. And then this is kind of why these things matter. So high end was something that really got to me, and we documented it in this Lander Garden Camargo sidebar in the State of the Climate. And who knows what high end, like the relationship that individual storm had with climate. It killed a lot of people in the Philippines and in Vietnam and China. And but it was weird in that it had the strongest wind speeds at the time ever assigned to a tropical cyclone. It was really rare that it developed so strong, so close to the equator. It made landfall at a record-setting intensity, and then the basin was nuts that year. And so all of these things kind of come together when you had what at the time was the warmest Pacific Ocean on record, when at the time was the highest sea level on record in that part of the world, and the strongest storm that was observed in that part of the world. A lot of people were killed by this storm. And I think when you talk about climate and events, there's no single driver. You know, we get locked into this. We try to find the DNA of climate change in every event, but it's usually a manifestation of multiple factors, some of which, in this case, clearly, at least short-term climate change made a huge impact on the outcome. And but it's a multitude of factors. It's a tough nut to crack. It's not a particularly clean thing to do in science, and it's really challenging in the 25 seconds or so that you might be given to talk about it. So if you feel like it's messy, it is. And if there's a way in your own community to maybe tackle these things, and I know there's some organizations, some nonprofits, and some for-profits that are trying to do a better job of reaching you guys with climate information, and I would suggest to continue to pursue those, because you're important. You're the only real trustworthy, like I said, you don't go into a bar and say, I'm a government climatologist, who wants to learn from me, right? But you guys do have that level of trust, and I think the more you dedicate to the compendia like this, I think the better off we all are. Yes, sir.
Greg Fischel, WRAL Raleigh. Do you think it's important, and I'm thinking of one group here, and I'm not going to mention a name, but it seems like everything they put out has a human fingerprint on it. And might it help if every once in a while there was some issue, or there was some phenomenon that, some natural cycle in the climate that they said, now here's an example of something that's always happened, still happens, but we can't attribute any human fingerprint to it, because I think it might detract from some people thinking that they're an advocacy group.
So I regret I cut a slide out of Stephanie's package that she gave me. One of her slides was just the roster of 2015's events. And there were 3 or 4 that basically they determined climate change had nothing to do with those events. And it's all in that BAMS explaining extreme events, which again, that's tough, it's nerdy, it's hard to consume, much less reinterpret. However, they do a nice job in the executive summary of kind of a roster of kind of a thumbs up, thumbs down. And they did find several events that were big events, that were events where me not being an expert in that way of thinking would probably, I wouldn't say this out loud, but if my wife asked me when we were lying in bed one night, I would say, yeah, I think that one probably had something to do with climate change. And then they showed that it didn't. So I think just that exercise itself, and it's a bummer because it was one of the last slides I cut. They did just that. Okay. That it's not it's not the boogeyman that's in every single thing that we observe, but that they have ways of trying to parse it out. Okay. That's a great question. Thank you. This just came out this morning. Again, inland flooding had a big year, and again, it's consistent with what we see, increasing trends in big rains. And then finally, and these are my last 2 or 3 slides, Dave. This is a model, and it's a complex model of everything that you're going to need to know if you're, quote, doing something about climate change. You need to know water. All of these climate change events are going to have something to do with water. Almost all are going to have something to do with poverty or the ways and the wheres where people live, and then there'll be other stuff. So that's my complex model of, almost every climate story will have water and poverty, and then this dotted oval is kind of the things that make us experts in different parts of the meteorological sciences. I've seen that over and over and over and over and over in my 8 years at NOAA. And we're not charged to talk about poverty, but every time we write a horrible event, I'll just say, the flash flood never ravages the nice part of town. Let's put it that way. And you take that and you reframe it around the globe, and you see a lot of people that are exposed to some of these consequences of climate change that don't really have a lot of power to fight back against them. Yes, sir.
Ken from St. Louis. I'm a little surprised that politics isn't pointed to in that graphic. I don't suspect it's among other things. I would think that it would have a huge role.
Yeah, so, and this is, we're gun shy about politics because we are scorekeepers ultimately. Like that's the 15 people that I showed on this slide. Our job is to keep score, and so we're not the referees, we're the scorekeepers. And it is a big topic for discussion in politics, but we kind of recuse ourselves of that. We can't afford to undermine the integrity of what we do by being involved in a discussion about things that are beyond our expertise.
I understand that, but I think that needing to know and wanting to do something, you have to take that into account. And
Yeah.
that's not making a statement in regards to any political leanings. It's just politics is going to be a huge issue when it comes to tackling climate problems.
So, yeah, and that's why I put this slide in here. No, I got 2 minutes. Is that all right?
But see, we react to politics in other parts of the world. Look what with what we've done with China and the discussions we've had with China. We react to what they refuse to react to, and they do the same. I think it's probably the big question mark in all of this.
So can I finish with a story?
I'm sorry.
No problem. No. That's why I put the slide on there. So here's a story. I'm from Oklahoma. You may have figured it out from my accent. And we have a significant climate episode in our past. So there it is, April 14th, 1935, Ruination Day, the big one. And you've heard a lot of stories, and they're true, about how this dust bowl just destroyed the fabric of our state and left scars in my native state that have either not healed or have healed in really odd ways. And they wrote novels about how horrible this time was. So I'm going to tell you a quick story. I was pursuing a PhD in adult education a few years back. Long story, I won't get into it. But one of the people I interviewed in my How Did You Deal with the Dust Bowl was a lady named Idris Grubus. And that is her as the kid that's standing. And this is probably her sister Gladys Grubus, and this is probably her birth mother. And her name was Lottie. So this was during the good times. The Dust Bowl came and broke this family up, and she never saw Ludi again. Not Lottie, Ludi. And Idris and Gladys kind of got handed off from family to family to family to family to relative to neighbor, and she spent basically her preteen and teenage years where her one mission in life was to make sure she didn't lose Gladys, because she was in some crappy situations with some bad dudes in her life, and it was not an easy story for a 13-year-old girl in Oklahoma trying to make it. She ended up, I knew her as Vivian. She was my grandmother. She changed her name to kind of turn the page on that chapter in her life. And if you were to ask a climatologist to analyze the Oklahoma drought record, and we'll get back to Vivian, they would clearly see the drought that tore the state apart, that caused little girls to have tough lives, that caused scars on the state, and they would easily pick it out as the 1950s. So that was the drought of record from the part of the state that Idris, later Vivian, grew up in. And so I want to pause on this point, because this is where you come in. There's a reason that they didn't write novels about the suffering in the droughts of the 50s. And that's because, and this is whatever part of the political spectrum you're on, things were better in the 50s than they were in the 30s. We managed the land better as agriculture. We managed our local economies better. We believed in institutions way more in the 50s than we did in the 30s. Family values wasn't exactly a great thing in the 30s, but a lot of this kind of traditional relationships among people that saw the world differently in the 50s helped. And we had better technical knowledge on how to manage the land, and we had systems in place to hold people that were struggling up. And Idris and Vivian, she never stopped being poor. but she went through this drought in the 50s in a farm town in Oklahoma, and her family stayed intact. And one of those kids that she had was my mom, and I am standing here today because we as a society got it right from that generation, from one generation to the next, from the 1930s to the 1950s. The sons and daughters that went through all the crap in the 30s didn't go through it in the 50s because we were better at life. And you're a big part in this climate issue, which is often laced with hostile discussion and the spewing and fire hosing of values and opinions at each other. You play a role to connect us with science that a lot of us don't. And I think it's so important that you're here. And you don't have to give your lecture and get on a soapbox. But the more you can help Randy Red and Billy Blue see the same information at the same time through the words and the graphics that you speak, I think you're going to help connect us a lot more. I owe my livelihood to the fact that the good news and the bad news, it took a generation to help repair a lot of situations in families in Oklahoma. That's the bad news. The good news is it only took a generation. And I think with our attitudes toward climate and the consequences that we see, you hold a lot of capacity to make the world better. And I'll stop there.
We're just about out of time, but I didn't know if anybody had any final questions before we break. And I also wanted to let the online audience know, and Deke, I'll just stand up here next to you, that's okay, is that on Wednesday night, so not tomorrow night, but Wednesday night, we're having a town hall meeting here at the Doubletree Hotel in Breckenridge, where we invite the public to come in, to sit in this room, and to ask questions of the speakers that will still be here on Wednesday. So it's a great opportunity for them to sit here and ask questions. And for you who are watching online, if you have questions as well from any of the speakers that were here, that will be here on Wednesday night for the panel, to just ask your science-type questions. And that'll be very, very welcome. So any other questions in the room? We have Greg and then Jennifer.
Greg Fischel, WRAL Raleigh. This is almost anticlimactic after what you just said. But one of the things that we have just experimented with at WRAL is that we've taken a look at that detailed CLIMO, the normals file, and said, okay, if the normal high is 50 on January 1st and one standard deviation is 10 degrees, that we're going to say that a normal range is 40 to 60. And that, you know, and then if it's more than 2 standard deviations from the mean, that's, you know, qualifies as being truly unusual, to try to get away from this thing of, oh, it was 52 today, that's above normal.
Yeah.
Is it really? You know, should we be talking more about a normal range as opposed to a specific number?
I couldn't agree with you more. And we have this kind of mantra in climate monitoring. We report the numbers, we report the anomalies, the difference from some baseline, and then we report the unusualness. And that's what you're getting at. So that's why we have the anomaly map and the percentiles map. You know, where does this stand in history? Trends and then impacts are the other things that we try to get to. But yeah, the unusual, you know, if the day's 3 degrees above normal, that's normal, you know, like, but absolutely. If there's a way to capture unusualness that again helps kind of tamp down some of the noise that people hear, you know, yeah, I think it's great.
Do you have a suggestion on specific thresholds to use, like percentiles or deviations or whatever?
So not offhand. We use this middle third, outer 10% kind of metric. There's nothing, it's served us very well. There's nothing perfect about that. It was a fairly arbitrary choice.
Okay.
Yeah.
Thanks, Pete.
Yeah.
I have more of a comment, Jennifer Covina from WPSD, and this is just my own sentiments. If anyone else shares this, I would encourage them to say the same to you, but don't ever don't ever disconnect yourself from the message that you just gave us, because that makes us all human and inspires us to continue on this journey of communicating with the public. I don't know how often you speak to broadcast meteorologists, but more and more the public is looking to us, as John Morales has written, as us as station scientists. We're the go-to public figure that the daily viewer sees. And we need that inspiration because it can be tough sometimes.
Yeah, sure. You have
really
it.
tough. But, you know, I very well may take that last section and post it on my page so that everyone can hear that watches me. And that's why I come here, to be inspired to continue the message. So I thank you for saying
Yeah,
that.
you bet. Thanks.
Thank you very much.